I want to talk about optimal tuning of subsampling Hamiltonian Monte Carlo, which is quite a mouthful. And I've got some, and these are my collaborators in a number of works on this. And basically, if you take away the title, what we were interested in, and I guess Tamara Broderick is doing a really fantastic job at it as well, we were interested to see if in some sense we can speed up MCMC computations by, you can do whatever you like with it, but well, you can even go into the pocket. Oh, this is great. You can even go into the pocket. Yeah. Okay.
Okay. Let's go.
We work as a team in different places.
This one?
Yeah.
This one?
That's great. And I'll pay you after the talk. It's a really good experience, but. They'll ask me how was the talk, but the talk wasn't that good, but the experience was great. And so we were interested in doing subsampling to compute margin likelihoods, to do MCMC and things like that. And but today I want to talk about subsampling when we want to get not an approximate answer, but an exact answer using MCMC. And I'll explain what sort of things we're covering. But so the basic overview will be Hamiltonian Monte Carlo. I'll talk about Hamiltonian Monte Carlo with energy conserving subsampling, block Poisson estimation to get unbiased likelihoods, signed Hamiltonian Monte Carlo, optimal tuning, and some empirical results. So the Metropolis Hastings algorithm is used a lot in predominantly used in Bayesian analysis, and basically you compute. This is what it's like. You compute the likelihood, you compute the prior, and theta p is your current proposal. Theta p minus 1 is your previous iterate, and then there's magic in Metropolis Hastings because you correct for any errors by doing the computing the acceptance probability. So with probability alpha, you set the new theta to the proposed theta, and you set the new theta to the previous iterate otherwise. Okay, so what we're interested in, that doesn't mean we do it, but what we're interested in is problems where likelihood evaluation can be costly. Now, likelihood evaluation can be costly for a number of reasons. The first one, which is the bottom one, is we've got lots of observations. Likelihood evaluation can be costly even when you don't have that many observations. If it's very expensive to compute the likelihood, like doubly intractable problems with costly normalizations, constants, exponential random graph models. It could be because you've got high dimensional problems, and it could be because you've got the model is a differential equation and you have to integrate it. So basically the theme of this, and what we try to do, maybe somewhat successfully, is to actually tackle problems where the likelihood is expensive. And one area where it's expensive is when there's lots of data. So the thing is, we want to do it exactly, compare it to the way we do it approximately, and also be able, so when there's lots of data, it's expensive. When it's expensive to compute the likelihood, this stuff also will apply. Okay, so one reason that things are difficult with Metropolis Hastings is that in high dimensions, if you take things like random walk, it's not very efficient, especially in high dimensions. Now, we put this slide here because later on we're going to be talking about estimating the likelihood rather than just evaluating it. And there you can't do all that much in pseudo-marginal stuff. So one challenge is high dimensional theta. One solution to high dimensional theta is to use Hamiltonian Monte Carlo, where you introduce a latent variable, which is the momentum variable, and now you expand the space, so you've now got an augmented posterior with theta and r in it, where r is the momentum variable, and you define this pi bar theta r as the augmented target. And what you do is you use Hamiltonian dynamics in order to move around the space much more efficiently. I won't have time to actually go through it, but these are the equations, and these are the idealized equations, because normally you can't just solve these differential equations. You've got to approximate them, but the properties of Hamiltonian Monte Carlo is that it's reversible, it's volume preserving, and it's energy conserving. That means the Metropolis Hastings acceptance probability is 1. In practice, you've got to do the Hamiltonian in discrete time. You've got to use a leapfrog. You take L steps with a size of epsilon. The Metropolis Hastings probability, acceptance probability, is no longer 1. One of the other problems, big problem, is that when theta is very large, then you need to compute not just the likelihood for this, but you need to compute the first derivative of the log likelihood or log posterior. And if you've got many parameters, that's very expensive, because you've got to compute at for each iteration, you've got to, if you've got 80 parameters, you've got an 80-dimensional derivative. If you want to do some Riemannian stuff, instead of Hamiltonian, you need the second derivative as well. So it's expensive. So one naive solution is to do the Hamiltonian dynamics on a subset, and then when you reach the endpoint of your the dynamics, you plug it into the Metropolis Hastings. Now the problem is that in doing that, you'll get a terrible acceptance probability, because, and people have done that, but you'll get a terrible acceptance probability because the Metropolis Hastings, the likelihoods in the Metropolis Hastings are not going to be the same as the likelihoods that you're using in the sampling, in the small sample that you're using to get the derivatives. So our solution, and I'll point you to the paper, our solution was to use ideas from MCMC, and instead of getting the likelihood exactly, we subsampled the likelihood, the log likelihood. So the log likelihood is a sum of terms, so we subsample that, and we get an unbiased estimate of the log likelihood. And in the approximate stuff, we corrected that to get an approximately unbiased likelihood. So the likelihood estimator, so we estimate the log likelihood unbiasedly, and then we correct, because just because you've got an unbiased estimate of the likelihood, a log likelihood, doesn't mean you've got an unbiased estimate of the likelihood. And that's what we want to, we want to do a bias correction, and we also use control variates to get an unbiased estimate of the likelihood, which then fits into a pseudo-marginal scheme. And at the end, I'll give you some references to see what we do exactly. And so now what we've got is so now we've got this, the U's represent, notice down here, we've got L hat. L hat is a sum over a subsample of the YI. So it's a small subsample. Later on, I'll talk about an example with 4 million observations, and our subsample is like 1,000, or it could be even 500. So what we do is we subsample, and in each iteration of the MCMC, the subsample differs. Tell me the time. How am I doing? What's that? This is 40. This is the second keynote. So this will take. Give me your initial offer, and then I will.
20 minutes.
What's that? It's 20 minutes. I don't need. So the initial offer is a good one. So basically, what you see here is that we've got L hat theta U, and that's based on a subsample in such a way we do simple random sampling. So we get a sample of M, that could be, we'll show you later some results, we get a sample of M, say 1,000 out of 4 million. So we've got a small sample of this, and our sample differs each time, so we get an unbiased estimate of the likelihood. We're also using control variates to reduce the variance. Okay, so now we've got, so this slide actually talks about pseudo-marginal. So pseudo-marginal is a technique where you don't have the likelihood, you get an unbiased estimate of the likelihood, and you work with an unbiased estimator. So I don't have the momentum things here. We'll introduce them in a minute. So basically, our ideas are formed around pseudo-marginal, where you've got theta, which are the parameters, and u, which indicate which observations are in the sample and which are not. So we're iterating theta and u, iterate for I equals 2 to n, and now, exactly like we do in the Metropolis Hastings, we accept or reject a particular u and theta using Metropolis Hastings. The only difference is that we're estimating the likelihood instead of evaluating it exactly. And we can show that we're targeting a distribution in theta and u whose marginal is the posterior of theta. So pseudo-marginal uses, well, the common form of pseudo-marginal uses unbiased estimators of the likelihood to actually achieve iterates from the correct likelihood. And, but one of the things that's crucial in pseudo-marginal is that the variance of L hat, I'll correct that in a minute, but the variance of L hat is not too large. Because you can imagine that if the variance of L hat is very large, and you get something with a high, so you can have a L hat that's very large, not because L is large, but simply because of the error you've got. So it's important so the drawback of pseudo-marginal is that you've got to control the variance of the likelihood, which I'll correct that in a minute for efficient sampling. Now, what we do is we use a form of pseudo-marginal on an extended target. So now our target is theta, which are the parameters, then the momentum, and then the u's, which are the indicators of which of the observations, which 1,000 observations out of the sample of 4 million, say, we're actually using at this point in time. Now, when we define this extended target, the key is that the marginal of this extended target, the marginal in theta of pi bar theta r and u is just pi of theta. So the key is that the marginal is exactly what we want. We get iterates from the right posterior, and that's the key with it. And our scheme is to do Hamiltonian Monte Carlo within Gibbs. So that means that we generate theta and r using Hamiltonian Monte Carlo given u. So given a subsample of 1,000, we use Hamiltonian Monte Carlo to generate theta and the momentum. So that's just like ordinary HMC, but now on a subsample. And then we generate u using a Metropolis Hastings update, so that we're using a sort of like a pseudo-marginal step. And it's crucial that the same L hat is used in the Hamiltonian dynamics and the Metropolis Hastings probability. That's why we call it subsampling conserves energy. A Hamiltonian Monte Carlo that with energy conserving subsampling. This way we can get distant proposals for theta quite efficiently. Now, so we've got an unbiased estimate of the log likelihood, but we want to do exact Bayesian stuff, so we need an unbiased estimate of the likelihood itself. And then what we do is we use what's called a Poisson estimator. We use what's called a Poisson estimator to get an unbiased estimate. And this Poisson estimator is of the form given above, more or less, but we've got a block Poisson because that's more efficient. So if our subsample is of size 1,000, we might take 50 subsamples, each of size 20, and then perform this estimator. So blocking. So instead of taking a whole subsample of size 1,000 and correcting it for bias, we block it up to give us more efficient estimation in terms of variance. Okay, so that by having an unbiased estimate of the likelihood, we ensure that our answer is exactly correct because we're using unbiased estimate of the likelihood. Now, what matters in Metropolis Hasty, in pseudo-marginal, when we do it, is that the log of the ratio of the densities in the top and the bottom doesn't have large variance. So what we do as well, we do a form of the correlated pseudo-marginal, which means that when we have 1,000 and we swap the subsamples around, we don't take a new subsample of 1,000. If we have, say, 50 samples of size 20, then we might change one of those 50, retain the other 19, and just hold on to one. So that means the U's in the top and the bottom are all the same except for 20 of them. And that gives us very high correlation between the U indicators. They indicate which observations we're selecting. Most of them stay the same on the top and the bottom, and that ensures that the likelihoods at the top and the bottom are highly correlated. So the logs, the log of the ratio is the difference of the logs. That means the difference of the logs is highly correlated, and therefore the variance, positively correlated, and therefore the variance of the log is going to be quite small. And we do it not through the correlated stuff, but we do it just by, we've got 50, we've got a block of 1,000, so we've got 50 times 20, and we change one of those subblocks, just change 20 of them and leave the rest. So we get highly correlated stuff. And so that sort of says, okay, we can use, because now we are, here what we're doing is we're using pseudo-marginal to select the indicators. So we get high acceptance probabilities. And now you will see as well that if you get an unbiased estimator for the likelihood, what I said was that then you can conduct pseudo-marginal. And that's not quite correct because not only do you need the likelihood estimate to be unbiased, but you need it to be non-negative. So here we are subtracting A from all the L hat, the little estimates of the little contributions for the log likelihood, in such a way, we would like to do it in such a way that the final likelihood estimate using the Poisson is all non-negative. But that proves to be useless because basically that means that it's very hard to select an A such that all the products are positive. So what we want to select is we want to select an A such that with high probability L hat is positive, but not with probability 1. So positive, so we want L hats to be, little L hats to be HL, greater than A, with with high probability. Okay, so we do a soft lower bound with probability of L hat, LM hat, HL greater than 0, close to 1. So now sometimes we get negative values. So what we do, we run an MCMC on the sign value. So we don't run an MCMC with LB hat. We run an MCMC with the absolute value of LB hat. And then we do importance sampling to correct for the fact that we are using, so to get, for example, in the posterior expectation of a function psi of theta, S is the sine of LB hat, so we run important sampling to correct for that. And that sort of gives us an exact result, not for the whole distribution of theta, but for any function of theta. And then we just do the usual HMC. Now we want to find optimal lambda. Lambda is the number of terms. We want to find optimal lambda and m, etc. to choose. So we define computing time. Computing time takes into account the inefficiency as well as the runtime. Something could run very fast but be very inefficient in terms of the integrated autocorrelation. So we've got this optimal computing time that we define in this way, where Tor is the probability of being positive. So we've got m lambda inefficiency by 2 Tor minus 1 squared, where Tor is the probability, and we want to optimize that if we can. So optimal lambda and m balance the cost of computing LB hat, which is m lambda on average, Metropolis Hastings inefficiency, and also the probability of a positive sign, right? So that so we need inefficiency, we need the variance, and we need the probability of positive sign, and then we optimize to get some optimal value, and so that we need to assume some sort of distribution on the L hat HL. So we can posit that to be normal, or we can posit it to be a mixture of normals. And we base part of our theory on a previous paper that I was involved in, 2012, we've got to perturb the theory. The derivation of IF is an extension of theory that we did before. So we've got idealized assumptions. Either the L hats, the little L hats, are normal, or they're mixtures of normals. And then what we can do we can use some results by Feller and others to actually compute, under idealized assumptions, we can compute optimal m and lambda to give us the smallest amount of computing time. And so I won't go necessarily into that, except that we can get, under some idealized assumptions, we can get exact results for that, because if LMH is normal, for example, then sigma squared is the variance of a random sum of log of non-central chi-squared, so we can compute that. Non-central chi-squareds are Poisson, etc. And we can compute stuff so that so basically what I'm saying is that we can tune the selection of the number of subblocks and the subsample size in such a way that we get optimal results for this situation. And so I'll skip all that. So I'm going to talk about just an example now. How am I doing for time? 10 minutes. I won't need 10 minutes, but what's that? Less is better. Unless I can borrow Leah's slides and then I can go through that again. No, so I've got firm bankruptcy data. I've got 4,748,000 and firm year observations. I've got and the subsample size that we take is 1,000. And the reason we sort of and therefore we need subsample sizes of and we can sort of figure out that we actually don't use the mixture of normals to do the little batch distributions, because we sort of say we're going to take the subsample size to be 20 or 30 or something, so we can approximate by normal. So the relative computing time, our performance measure, is computing time of our approach versus the computing time of what we call the perturbed Hamiltonian Monte Carlo with energy-conserving subsampling. That's another version of the stuff that we've done that's appeared in JESA now. And so there we get a good approximation, but it's not exact. And okay, so now we look at, so we've got 81 parameters we've got an 81 parameter logistic regression. And we're gonna do everything relative to, and so minimum says this is the minimum relative computing time, for the minimum for the thing that's got the smallest computing time. Median means a parameter that's got medium computing time, and max means the parameter that had maximum computing time. So Hamiltonian with minimum, Hamiltonian Monte Carlo direct on all the data is 358 times less efficient than with energy conserving subsampling, and then on the minimum and then on the median it's 2.2. Now, so HMC ECS is the stuff with energy conserving subsampling, our algorithm, so that denotes it as 1. SG HMC1 is a stochastic gradient HMC from the machine learning literature, and SG HMC2 is second stochastic gradient HMC, and I'm sure Tamara will say they're no good, and in fact they're no good. And then SGLD is a stochastic gradient with Langevin diffusions. And you can see that we are quite a lot faster than HMC itself. So so this just demonstrates that we're reasonable. It's not, and this is exact. Now I'm going to show you, the last plot I'm going to show you is some of the posterior density plots. Oops. Oh, now you can still see it. So I'm going to show you some of the density plots. So the first line is the first row is the perturbed density plots. That's from our, when I talk about perturbed, I mean that because we're using approximation, the target is perturbed, and we do MCMC on that, so we converge to a slightly perturbed target. The second row is the energy conserving subsampling. That's what we've got. The third row is L1. And the fourth row is the stochastic gradient HMC1, HMC2. That's the third and fourth row. And the final row is the SGLD. Now, our computing time did not take account at all of the fact that some estimates are bad. All it does is it looks at inefficiency of the chain and also computing time. It does not take into account that, so if the efficiency is high, you're going to get bad computing times, but it doesn't, but you can see the SGLD stuff is terrible, and that's not reflected in the fact that it's slow as well, but it just looks terrible. Okay, so basically, okay, so conclusions. We've got subsampling to speed up MCMC and HMC. Block Poisson gives us unbiased estimation. We tune the signed HMC. We've got light speed ups, and what we're working on now is basically various approaches for sort of tackling doubly intractable problems, because with the stuff Girolami's got in his papers, it's very easy to augment some variables and use these sort of techniques as well. So the aim here was, just to do the stuff exactly. So basically the first reference, these are some references. The first one is just to the perturbed subsampling paper. The third one is a reference to the pseudo-marginal approach. That's a really good paper by Andrew and Roberts back in 2009. The fourth paper is really the paper I talked about now. Oh no, the fifth paper is that. So what's the fourth paper? A paper that sort of dealt with signed HMC, the signed MCMC is by Lyon, Girolami, and two other authors. And okay, the first derivation of this pseudo-marginal that said that the optimal sigma was 1 for the variance of the likelihood is the 2012 paper in Journal of Econometrics, and that's all I have to say.